In this video, we're going to talk about error correcting codes, how we can get around some of the errors that channels may introduce. So we're going to talk about one as a very simplest one called the repetition code, and then we're going to go on to a much more interesting and much more useful code, actually a class of codes called Hamming codes. Let's go through and see what I mean by error correction. So here again is the digital communication model that we've had before, but there's a new thing that has been stuck in here. So we've already talked about source coding and how to do compression and represent the source letters efficiently with bits. Now what's going to happen, the channel coder is going to be placed here so that it converts what we're going to call data bits into more bits that have a very special structure, so that by the time these bits arrive and go out of the channel where errors can be introduced, the channel decoder can repair those errors and hopefully produce something that's the same as the data bits produced by the source coder. So this may seem like magic. How can we compensate for errors that the channel introduces after they've occurred? And that's it's actually pretty straightforward to see how you can do that, but generating efficient error correcting codes is somewhat tricky. So can we mitigate channel induced errors? Absolutely. And these lead to the error correcting codes, which are commonly known as ECC. So the simplest error correcting code is the repetition code. It's pretty easy. So you take, for each bit produced out of the source coder, you repeat it, in this case 3 times. So a 0 data bit becomes 3 data bits in what we're going to call the code word. And if the data bit is a 1, we produce 3 bits that are 111. We just repeat them. That's why it's called a repetition code. So this actually helps. In more detail about what's going on is that you have this little drawing here. We have a sequence of data bits. It looks like I've got here a 1, 0, and a 1. And if we went through our digital transmitter and worried about a BPSK baseband signal set, that might produce something that looks like that. Well, now, if you take that same sequence and go through the channel coder, it's going to repeat the bits. So now we have 1, 1, 1, 0, 0, 0, 1, 1, and 1. One of the ones got chopped off. And when that goes through the transmitter, we now have individual bits, and the correlation receiver knows those are individual bits and is going to try to figure out what each individual bit is. So now there's a PE for every one of those new bits. All right. So this creates what is called an N1 code. So we're repeating each source bit n times. So for every data bit that comes in, we're producing n bits. So that's what the n comma 1 means. 1 bit in, n, capital N bits out in the code. Now the other thing that's important here, will be important in applications, is this has what's known as a code rate, which is the same as re-expression of this. It says that for every bit in, I have to send capital N bits. So it has, in the case of our repetition code, has a rate of 1/3, which we're going to see is a little on the low side. But this code can correct all single bit errors. Now, let me show you how that works. And what we're going to do is decode by majority vote. So here's the idea, and this is why the number of bits in and a repetition code is odd because we're going to vote. So let's say that the source bit, the data bit, was a 0. We're sending 3 bits, so there are 8 possible received code words that could come in out of the channel. All the bits could come out correctly and no changes, and so we say it's a 0 because we're going to raise our hands and vote. I'll say 0, I'll say 1, pick the one with the most votes. So here's a case where 1 bit got flipped. And what it's going to do is still majority 0, so it corrects the error. So this is how you can correct errors after they have occurred, and that's because you've just repeated the same thing several times. So if you go down this list, you see there are times it's possible that 2 bits occurred in error, and the error correcting code is not going to be able to correct it. And so that's why this is a single bit error correcting code. It can correct 1 bit in error, but not 2 or 3. So that turns out to be an accomplishment. So for all the 8 possibilities of received code words, we can correct 1, 2, 3, 4 of those code words and understand and say that a 0 is actually sent. And we get it wrong 4 times. And the same thing's going to happen when a 1 is sent. We're going to be able to correct the error for 4 of the code words and be wrong for the other 4. So what's the probability now that the data bit is decoded wrong? So that's going to be the sum of the probabilities for the cases in which an error still occurs. And that's just add those up and you get that for an expression. So the question is, do we win? Is this probability what's called a decoding error? We don't get the original data bit back. Is that probability bigger or smaller than PE? In other words, the situation in which we send only 1 bit, which is what we would do if we had no error correction. It had better be smaller. And it turns out it is. You can show that if PE is less than a half, that this quantity is always less than PE, and sometimes much, much less. If PE is like 1,000th, 10 to the minus 3, notice this square over here. And that's going to be probably the dominant term, and so at 1,000th, this probability here is roughly 3 times 10 to the minus 6. So we can really reduce the probability of error by adding error correcting bits. So let's go over what a repetition code is. It's a very simple code, not just repeat the bits, very easy to do, but it has some downsides. One, it has a very low coding rate, 1 over n. And we're going to discover in just a second a error correcting code that has a much higher rate and still corrects all single bit errors. Note that as n increases, the probability of just getting 1 bit in error actually becomes smaller than the probability of getting 2 bits in error or 3 bits in error. And that's just because you keep flipping coins a lot. You're going to not just wind up with just 1 bit in error, and that's all the repetition code can do, is just correct 1 bit in error. So we definitely need more powerful codes. Well, let's talk about one. But first we need to know about what are called block codes, and this is a generalization of the repetition code. Repetition code is a special case of a block code. So here what we're going to do is take in a block of k source bits at once, and what we're going to put through the channel are n bits derived from those k. So in the case of the repetition code, we took in 1 bit and put out n. More generally, we're going to try to take in more than 1 bit at a time and put out n, and that's an nk code. And that's why I wrote before that the repetition code was an n1 code, special case. And here's an example of a 7-4 code, which, as you might expect, has some pretty good properties, and we're going to see that as we go through. So here's what it does. It's trying to put out a code word of 7 bits. Here's a list of the bits, and here's a mathematical description of how they are related to the data bits. The first 4 bits simply repeat the data bits, so they're exactly the same. And then for bits 5, 6, and 7, they are given by, it turns out, sums of the data bits, of particular data bits. Now what that O with a circle around, plus with the circle around it means exclusive OR. It's essentially addition in binary arithmetic when there's no carries. So 0 exclusive OR 0 is 0, 1 exclusive OR 1 is 0. It's only when the 2 bits disagree do you get a 1. And so you may have 3 bits here that get quote-unquote added together, but the result is only going to be 1 bit. And so no matter what the data bits are, you just apply these formulas, and that derives the 3 bits we get, you might say, extra. We have 4 data bits coming through as they are, and then we derive 3 more bits from those. It turns out these are good bits to derive, it turns out. So we got to figure out how can we prove that the code I just wrote, that 7-4 code, actually can correct errors. So we need to go and figure out a little bit more about error correcting codes and how to think about them. And the key to that is something called the Hamming distance. So Richard Hamming was a Bell Labs engineer, and he developed a whole sequence of things, the Hamming distance, and it turns out that 7-4 code is a special case of a Hamming code family. So he worked on this a lot. So we're going to define the distance between 2 code words as being a sum, and I really mean sum here, of C1 exclusive OR C2. So you're going to get in bits out of this. The sum, what that's going to be is this, it means how many ones are there in that result. So you exclusive OR these 2 things together, and then you tell me how many ones there are. That's what sum means. Sum means think about them as actual 1 and 0, not binary numbers. So let's take an example. Suppose I have 2 code words, and I just pulled these out of the air. I want you to note that they differ in those 2 bits. Okay? So I claim these 2 code words are a distance 2 apart. They differ in 2 bits. Well, mathematically, we can see that if I add these 2 together, and you can test this for yourself, that the result is this. And remember, exclusive OR gives you a 1 only if the bits disagree. That's the key. And of course, the number of bits you have in there is 2. And so we know the distance between these code words is 2. Now I want to point out something that's going to be useful later on. We have this relationship here. If I take this and add it to C1, I will get C2. And I will also find that C1 is equal to C2 plus this binary sequence. This is going to be useful later on. Okay. Let's see why this is important. So distance is the Hamming distance assesses how far apart 2 code words are and how many bits have to be changed for one to equal to the other. So how far apart do 2 code words have to be so that in spite of the fact that there's a single bit error, I actually can figure out what the original code word was. How far do they have to be apart? And another way of saying that is, when can a single bit error in one code word not be confused as a single bit error in another code word? That would be a disaster. If we couldn't figure this out, then if a single bit error occurred, we wouldn't know what the original code word was, which means we wouldn't know the original data sequence. So they have to be far enough apart that an error in one code word is not confused with another code word. So I have a little geometric picture to show you so we can figure this out. So sort of abstractly, we have here two code words. We have C1 and C2, and of course they're different. Well, suppose I have a single bit error in C1, so I'm using E1 to represent some particular single bit error, which means this E sequence has a bunch of zeros with a 1 in one position. That's what the error position means. And that gives, once I add these two together, it gives me, let's say, that. Well, suppose it was possible that C2, if I add to it another single bit error sequence, gives me at the same place. So with these sums, the number of ones in E1 and E2 is each 1. How far apart are C1 and C2? Well, because I can get to C2 by taking C1, adding E1, and then if I add in E2, that's going to get me over here. That means, because these two each have a bit on, that when I exclusive OR them together, I get 2 bits, and the distance between them is 2. This would be a disaster in terms of error correction. This is not a code word in general, and it's 1 bit away from C1, it's 1 bit away from C2. I can't tell if C1 or C2 was the actual code word. I'm in big trouble. This kind of code, if it does not have a Hamming distance of greater than 2, I cannot correct single bit errors. So, what distance is good enough? I think it's pretty clear that we need to have a minimum distance between any possible pair of code words that's greater than 3. If it's greater than 3, that's fine, but 3's the threshold. And the idea is that if we have one code word here and another code word there, and an error takes us up here, well, an error might take this up here, and since these, let's say, are at least a distance 1 apart, at least, then they won't be confused, and I can get back to the original code word and correct that single bit error. So this is an important criterion for having a single bit error correcting code. And guess what? The repetition code satisfies that property. So there's only 2 code words because it only takes in 1 bit at a time. And so we add together those code words, we get 1, 1, 1, and the sum of those, that means there's 3 ones. So sure enough, this satisfies our criterion for a single bit error correcting code. Well, as it stands, I would have to find the distance between all possible pairs in an error correcting code and see what their distance is between them. Well, it turns out, because of the properties of block codes, there's a very efficient way of doing it, which actually provides some insight in what's going on. But to do so, I'm going to have to re-express these codes in terms of matrix notation. So we're going to take a little notational diversion, if you will. So we're going to say that the generation of a code word from a data block, a block of data bits, is given by this matrix equation, C equals GB. And G here stands for generator. This is called the generator matrix. And in the case of the repetition code, there's only 1 bit. because it's an N1 code. There's only one bit taken at a time. It puts out 3 bits, and the G that looks like that means simply repeat. If you think about it for a second, what does this mean for the case of something like this? When you have 1 bit in, it means just simply give it back. Well, let's look at our 7/4 code, which is a bit more complicated. So here's that code that I wrote before, same thing. And so now it's taking in a block of 4 data bits, putting out a block of 7 coded bits. And what G do I need to express this? And I claim it's pretty easy to do. So because this code just repeats the original data bits, the upper part of this matrix is the identity matrix, I, capital I, because that means just repeat the bits. The hard part, if you will, is down here, but that's pretty easy to do. You simply put a 1 in the generator matrix for the bits you want, in the position of the bits you want to select in your sum. So I've got 3 1s and then a 0. That means take data bits 1, 2, and 3. And the next one says take data bits 2, 3, and 4. Sure enough, that's what it is. Take data bits 1, 2, and 4, and that's what that is too. So this is a very concise way, this generator matrix is a very concise way of writing down what the code is, how it operates on the data bits. It's not clear you would actually implement it this way, but it's a nice mathematical way of doing it, as you can see in a second. And the reason it's important is because this code has really cool properties. In fact, it's linear. Really important here. So, because this is just a matrix multiplication, this code is linear. Suppose I add together 2 data bits sequences. Well, that's got to be some other data bit sequence. Who knows what it is, but it's something. Well, even though this is exclusive OR, it still obeys the distribution laws. This is GB1, exclusive OR with GB2. Well, by definition, that's C1 and that's C2, so it obeys the superposition principle. And that has all kinds of interesting consequences, because since B1 plus B2 is some other data bit sequence, in our 7/4 code, these are each 4-bit entries. We exclusive OR those 4-bit blocks together, we get some other 4-bit block. Well, that has to be some other data bit sequences. That turns out to be C3, which means it's a code word. So adding together 2 code words results in another code word. Well, that means that the distance between any 2 code words has got to be the same as the number of bits in some other code word. So we only need to examine individual code words, not pairs, but individual code words, to figure out the code's error correcting capability. We just need to examine how many 1s are there in every code word. And that tells us what the Hamming distances are between all possible pairs. So that's why I wanted to go into matrix notation to prove this linearity property. It's really important. So there's my generator matrix for my 7/4 code. I want to point out something. Suppose I have a 1-bit sequence, data bit sequence. What's the resulting code word for that? What you should find is that the resulting code word for that is the first column of G. If you have another single bit data block with the 1 in the second position, that corresponds to the second column, etc. So staring me in the face, in the columns of G are 4 code words. So all I have to do is count up the number of bits in each column, and sure enough, I'm a happy guy. They're all greater than 3. Well, that's 4 of the code words. Next thing I need to do is add together 2 columns to create more code words. Well, I want you to note, because of the construction of this code, you know that the upper part is going to have 2 bits. As long as every row, every pair here differs in at least 1 bit, I know that that's going to give me 1 down here. I've got 2 up here, so I have at least 3. And if you look at the way this bottom part was constructed, you look at all pairs, they differ in the bottom part in at least 1 place. So that means all pairs have 3 bits, have a number of bits of 3. And now if you add 3 of them together, you can see from the top you're going to get a 1 in all cases. So that gives me a length of 3. It doesn't matter what happens down below. So this is a single bit error correcting code. And that's because all the code words have at least 3 ones. The fact that one of them has 4 really doesn't help. It's the minimum of all these distances that matters for being able to have a single bit error correcting code. So, and I want to point out, as opposed to the repetition code, its efficiency is much higher. Repetition code that we talked about had a code rate of 1/3, pretty low, 1 bit in, 3 bits out. Now it's 4 bits in, 7 bits out. Much higher efficiency, and it too can correct single bit errors just as well as the repetition code. So, error correcting codes. Even though the channel introduces errors, the error correcting code can repair some of the errors. If more than 1 bit occur in error, our single bit error correcting codes can't correct them. But at least all single bit errors can be corrected. And I showed you with the repetition code that lowers the probability of the received bits being an error. This is very different than in analog communication. In that case, once the signal comes out of the channel, there's nothing you can do other than remove out-of-band noise. But you cannot remove the out-of-band noise by linear filtering. You are stuck with it. You can't do anything with it. Here, we're fixing errors and lowering the probability. We're essentially making the channel less noisy by adding error-correcting bits. Now, we must send bits at a higher rate than required by the source, but efficient codes, i.e. ones having a rate that's close to 1, are fairly easily designed, and we'll see that in the succeeding video. However, I do want to point out that error-correcting codes have limited capabilities. We can't fix double-bit errors. In fact, for the case of the repetition code and the Hamming code, I showed you that if a double-bit error occurs, we're going to think a single-bit error occurred, and we're going to correct it badly. We're going to make a mistake. And so longer code words, double-bit errors occur more frequently than single-bit errors, and that can be a problem. So in the next video, I'm going to talk about how you actually do the error correction for a Hamming code.